Labs at Intel. His research areas include electrical and optical I/O circuits, photonic devices and systems, prototype characterization and test methods, and linked system modeling and analysis tool and methodologies. So let me set up the video now and let's make sure it works. So here we go.
Hi, thanks for joining today. I'm James Jaussi, Director of the Phi Research Lab at Intel Labs. Today I'd like to share a vision of optical communication and bring that technology to core compute. It's really a journey and a story of making a transition from electrical to optical I/O. If we look at the overall performance within a data center, there are key bandwidth requirements, both in terms of the network as well as for the server. Switches, if we look specifically at those, it's interesting to know in the lower left-hand corner the performance requirements, both in terms of the aggregate bandwidth on a per switch, as well as the performance on a per lane basis. Note that the overall bandwidth on a per lane is actually at a lower rate than the performance of the aggregate performance of the switch. If we look specifically at the server and the number of cores versus a process technology, the number of cores continues to scale over time. That requirement really results in the need for additional bandwidth. One way to satisfy the overall performance and the bandwidth requirement is the increase in the number of pins or growth in the package. So if we look at the overall requirements for these two technologies, both in terms of the switch as well as for server packages, they both have very similar requirements in terms of the performance scaling, approximately doubling every 2 to 3 years. Now, in order to deliver this overall performance for servers, package pin counts is significantly increasing. As a result, this drives up cost in terms of the package size, as well as performance cost for sockets and routing and other interconnect requirements that support that particular socket or package. If we take an example and look closely at electrical and where electrical performance is today. In this particular slide, I'm looking at an electrical cable and its performance, and looking at an overall performance of around 200 gigabits per second. In this particular case, the electrical connection or the electrical cable is either a coax or a twinax. The approximate performance and reach of this at 200 gigabits per second is on the order of a meter, depending on the overall quality and the cost for that particular cable. Also noted on this slide as a function of length is multi-mode optics or multi-mode fiber and also single mode. Now it's interesting to note in terms of the overall performance that multi-mode optics can support additional bandwidth, potentially higher than 200 gigabits per second, primarily by leveraging multiple wavelengths. Similarly, if we look at the overall performance of a single mode fiber, it also can support multiple wavelengths. Now this technology relative to the application, there's a desire and there's effort going into improving the performance of the electrical connection and also making advancements, improvements of scaling the performance of multi-mode fiber as well as single mode, both in terms of scaling up and also in terms of scaling down. Now on the scaling down side of things, that really is about cost and the cost of the technology to operate and be cost effective over shorter distances. Again, one of the main core technologies in order to enable this in terms of bandwidth and future bandwidth scaling is multi-wavelength division multiplexing. And we'll talk quite a bit today about that and the importance that plays in the overall bandwidth scaling. Now with this context and this background, the question is why make a transition to optical? Why not just remain with electrical connections? One of the main motivations in part is tied to the reach of the interconnect, how far the cable or route can go at higher data rates. And the example that I illustrated today was focused primarily on a fiber or a cable, but this also applies to interconnect and routing within a board over packages, sockets, connectors, over much shorter distances. Those fundamental trade-offs still exist there, and that's primarily tied to the properties of loss or attenuation of the signal at higher data rates. That's a fundamental requirement or a fundamental property of electrical interconnect. Optical, on the other hand, there is not a loss as a function of frequency given over specific ranges or reach of that fiber. So really the question is well then why be motivated? Why make the transition? One of that is tied to two of them are tied specifically to energy efficiency and bandwidth per fiber. Today, the overall bandwidth efficiency, energy efficiency of an electrical interconnect, a serial interface, is on the order of around 5 picojoules per bit. Now, if this optical technology can provide a better energy efficiency, say for example a picojoule per bit, it essentially would be 5 times lower. That provides motivation to, in part, consider making that transition. If we look at the bandwidth per fiber, if we use that number of around 200 gigabits per second, that's something that allows us to look and to scale up to a terabit per second. Again, on the order of about 5 times better bandwidth per fiber. Both of these metrics in terms of the improvement, both on the energy efficiency and the bandwidth per fiber, really help motivate the transition. Now, that's just not enough in order to make that transition for those particular performance targets. There needs to be additional bandwidth scaling over multiple generations. The cost in order to transition to a new technology really wouldn't be justified if it was for a single generation. So multiple generations is a key part of the requirements in order to really make a transition to this new technology. In this particular case, I'm illustrating where it can scale for multiple generations up to 250 femtojoules per bit and also a terabit, 4 terabits per second per fiber. If we take a closer look at a server rack, in this particular topology, we're illustrating we've placed a Tor switch on the top of the rack. That switch connection between the leaf switch and the Tor switch is an optical connection. Within the rack, where we have multiple servers placed, are electrical connections that are routed up to the top of the switch. This is a general topology that really illustrates where the technology is today. And really our focus in part is looking at the overall performance of the Tor switch and that optical connection, and also connections within the server up to the Tor switch. So if we start to build out a data center network and look at multiple clusters of servers. So in this particular case, we've taken a rack, we've tiled that rack into groups or into clusters, and these clusters then are set side by side one another. Off of those Tor switches, then we build out a network that connects from the Tor switch to the leaf switch to the switch and ultimately up to a router as you go up through higher levels of the network in the hierarchy. All these connections here illustrated are optical connections. Now, should note this is a simplified diagram in part to help illustrate the overall topology and how this network can be built out. One thing that's interesting to note is the reach that are targeted for these different switches. It's on the order of 100 meters or more in terms of the reach requirements for this particular technology. As we look closer at the system architecture and where the network switch is, in this particular case, we've placed the network switch on top of the rack. There are a couple priorities that this switch is optimized for. Those priorities include cost and reach, bandwidth, power, and latency. All of these parameters are very important to track relative to the overall performance of the technology. Now, the exact order of the priorities really is going to depend on what the system is optimized for, but one of the main things for this network is reach, and being able to satisfy that reach within reasonable cost. Another important parameter is bandwidth. As we illustrated at the beginning of the presentation, bandwidth is approximately doubling every 2 to 3 years. So bandwidth is a crucial thing in order to deliver the overall performance required for the network. And of course, latency and power are also important. One thing that's interesting to note is the compatibility to existing standards that are currently in the market. This would be compatibility at a specific data rate And in this particular case, it'd be on the order of 112 gigabits per second, as well as 224 gigabits per second as we look to higher data rates. That compatibility with the current architectures and infrastructure is a very important requirement. If we look at taking the technology and really integrating optical technology into a switch, this is a demonstration of doing exactly that. This is something that was demonstrated back in 2020, where Intel took the technology of silicon photonics and integrated it onto a switch and demonstrated the capability of the co-packaged optics. In this particular case, bringing the core pieces of the technology onto the same package and being able then to deliver an interface with the particular protocols and be protocol compliant to the existing network. This really demonstrated the capability of integrating that technology and ultimately demonstrating the co-packaged optics concept as well as technology. So now I'd like to show a video that illustrates the data center network and really looks at the core technology and how the technology can be incorporated and brought and integrated into a server. This illustrates a network and an overall data center configuration where optical is used, and it makes the connections from the different Tor switch and rack switch and the overall communication infrastructure. But if we zoom in and look closely at bringing the technology close and into a package, conventional modulator technology was too large of a footprint. But by miniaturizing this technology using microrings, the footprint is much, much smaller. This allows us to incorporate a technology and miniaturize the overall footprint. What the technology does is it modulates the light from a laser source, as illustrated here, and it allows us to have support multiple wavelengths. So each ring, in this particular case, is tuned to a specific wavelength, and those wavelengths are allowed to operate simultaneously, one right next to another, because of the tuned circuitry of the rings. This allows us to multiplex and support much higher bandwidth on a per fiber basis using wavelength division multiplexing. Because of the footprint and the miniaturization, that allows us to scale these and have many lasers on a particular package, as well as potentially hundreds of rings. By so doing, this allows us to bring that technology close and integrated tightly with the package. And now we have optical communication, which can break out and route out directly from a server package. This allows us to really incorporate the overall technology and be able to communicate across the full data center. So if we look a little bit closer now at the compute interconnect. Before we were talking about the switch which is placed on top of the rack. Now let's go specifically inside the rack, similar to what the video illustrated. What it allows us to do is to look at the core building blocks and components associated with that, this particular topology. There are core CPUs, there's a fabric that's on within a package as part of that SoC, there's connection to memory, and ultimately I/O. Now the priorities for this particular technology is going to be different relative to the priorities in the network. Here, the overall performance and bandwidth that we need on a per lane basis is going to be lower in order to keep the overall power down compared to the system power or the available budget within a package and a CPU. So the priorities are different. In this particular case, it's going to be in the order of 32 to 64 gigabits in terms of, again, maximizing the overall energy efficiency and minimizing the power. If we look a little bit closer at the comparison of these two technologies, on the left-hand side, we have the compute interconnect, as I just finished illustrating and presenting. And on the right is the network. Now, it's very interesting to note where these different cost, reach, latency, power, and bandwidth density fall relative to the two different applications. On the right-hand side, the cost and the reach are much, much higher relative to the left-hand side. Now, the compute on the left-hand side is really, again, focused in part on electrical interconnect, as it is today. It's cents per gigabit per second in order to provide that cost in terms of what that technology costs. So really, in order to address and take a technology that is designed and been optimized for longer distances and these other parameters, these other metrics, really has to be brought into a system and address specifically these characteristics relative to the performance of that system. So for example, cost needs to come down significantly from gigabits per second to cents per gigabit per second. Latency needs to be reduced because there are applications that are latency sensitive. Power needs to go from tens of picojoules per bit to picojoules per bit. And bandwidth densities need to increase significantly. This is really the core part of the technology and the optimizations that need to be made in order to make the transition and bring this technology truly into a server platform and a server package. So we look at the overall fiber bandwidth projection and the trajectory of what this could be. As I mentioned earlier, one of the main things that we want to have is a technology that has the ability to scale over multiple generations. And in this particular case, I'm defining generation as a doubling of bandwidth each generation. So if we look at the lower left-hand side of this curve, what we're indicating is on the order of 8 wavelengths, very similar to what was illustrated in the video, all operating each one of those lanes per wavelength at 32 gigabits per second. Now that gives the initial entry point, if you will, relative to this first generation. From there, now what we can do is map out and include different technology optimizations, leveraging the properties of optical and the multi-wavelength division multiplexing technology in order to really scale and to improve the overall bandwidth on a generation by generation basis. So if we look at the second generation, the data rates can increase on a per lane basis. And the third generation, the number of wavelengths can increase. Another thing that can be done as we look at fiber and the characteristics of fiber is we can use 2 different polarizations in the fiber in order to double the effective bandwidth for each one of the polarizations. That gives us, again, the ability to double the overall bandwidth. And so on. We can continue to increase in terms of higher data rates and an increase in additional wavelengths. All of these different data and technology points really in part will be dictated based on what is optimum for a particular application or for a particular product. But the fundamental point of the technology and the ability to scale the technology is something that is important relative to the future performance over time. So if we transition and look at some interesting data points along this performance curve, this is an example of recent work looking at 4 wavelengths. This particular prototype has transmitters and receivers. It operates and interfaces with the microrings, as I introduced and discussed briefly earlier. And it's operating at 50 gigabits per second and 4 wavelengths. Now, this would be a point before the curve, but nonetheless, it illustrates the capability of the overall performance based on an aggregate bandwidth of around at 200 gigabits per second. Some additional data points which are interesting to note is the recent development of an 8-wavelength laser. This was also illustrated in the video as well. One of the important things to note here is the overall performance of the laser in terms of its wavelength spacing and also the uniformity of the amplitude on a per laser for each one of the wavelengths is extremely important. And it exceeds industry standards in terms of that performance, of those performance characteristics. Another thing that's really important to note is the fact that this laser is built on a production laser that's being sold in the market today. Let's pick up another point, another interesting data point. And this is work looking at a higher performance transmitter. It's operating at 112 gigabits per second. It includes the integrated laser, also the modulator, and ring thermal control in order to control the overall performance of the ring. This would give us a data point on this curve. Now, it's important to note that I'm not illustrating all of the technologies that are illustrated on this curve. I'm really picking out a single characteristic or a particular circuit to illustrate the fact that these are the fundamental building blocks that go into this technology that would build this, overall trajectory. If we move on and we look at another scenario, this is a high bandwidth amplifier on the receive side, or TIA, operating at 128 gigabits per second. So again, it moves us up this performance curve along these technologies that are being brought together to deliver this overall bandwidth. A very interesting point is a high-speed demonstration of a microring. In this particular case, using prototypes in the lab, using test equipment, we exercise the performance of the ring, scaling it all the way up to 224 gigabits per second. PAM4 modulation in this particular case. And it's interesting to note that relative to the line that was drawn, this is actually outside or beyond the line in terms of that overall performance. So this is an excellent example of the scalability and the overall performance capabilities of this particular technology. Another very interesting data point is the dual polarization. In this particular case, this is operating at 260 gigabits per second. There are two polarizations, a TE mode and a TM mode, both operating at 130 gigabits per second. And these are operating simultaneously over the same fiber, but different polarization. Again, allows us to double the overall bandwidth on a per fiber basis. So now we're going to take a step back and look at the chart and look at the overall performance of the line that I showed earlier. And in this particular case, I've added an additional curve. Recall the two things that we've been focusing on and highlighting has been the fiber bandwidth, the bandwidth per fiber, as well as energy efficiency. Now, on the previous chart, we're focused primarily on the bandwidth of the fiber. Now, I've added in energy efficiency. Now, one particular point of interest is a terabit per second per fiber, as well as a picojoule per bit energy efficiency. That's a point where the motivation to make this transition is significant because it exceeds what is being done today with electrical. Additionally, we have additional length that can be achieved once the data is inside the fiber. But that's not necessarily going to be the end of where this technology is going to go. Again, we need to scale to additional performance, higher data rates, better efficiency. And so another very interesting point is looking further out in time at a terabit per second per fiber and 250 femtojoules per bit energy efficiency. In fact, this is an important point for the work that we're doing at Intel and also in terms of a research center that we've set up that is targeting specifically these metrics and developing and focusing on the technologies that help pull the ingredients together in order to really demonstrate the core technology capability and the scaling of it. So this includes 7 different universities that focuses on the optical technology, both in terms of fiber coupling, lasers, microrings, integration of the photonics and the electronics, and pulling all the technologies together in order to really demonstrate this core capability of 4 terabits per second and 250 femtojoules per bit. So in summary, if we look at the technology and the opportunity for this technology, we're starting to see the transition of electrical to optical, primarily because of the challenges associated with scaling electrical. Now, I should point out that electrical is definitely a technology that's going to be around. It's going to be around for a long time. But making this transition to optical and really investing in the core scaling capability is a very exciting opportunity. And it also opens up the possibility of extending the overall performance in terms of reach and new topologies in terms of network that would come along with that technology. We talked about the multiple generations of scaling. That's a critical part. It's an essential piece of the overall technology, primarily because the investment needed to make the transition from electrical to optical, having multiple generation scalability is essential. And finally, highlighted some of the technologies that are in the pipeline and different core capabilities that have been demonstrated, both in terms of laser and multiple wavelength performance, rings, the overall performance of the rings, and also the dual polarization.
Hey everyone, please, if you have any questions,